Hello, thanks for watching this online module on ventilation for new homes. I'm Berkery from Southface, and in the next few minutes we're going to discuss requirements and strategies for ventilating new homes. This educational opportunity is made possible by funding from the Alabama Department of Economic and Community Affairs, Energy Division, and by the U.S. Department of Energy. What we will cover in this session include changes to the upcoming Alabama Residential Energy Code, a discussion of the relationship between ventilation and infiltration on projects, and strategies for achieving code compliance, tight homes, and adequate ventilation in residential projects. The new Alabama Commercial Energy Code will take effect on January 1st, 2016, and the new Alabama Residential Energy Code will take effect on October 1st, 2016. For more information about Energy Code adoption and Energy Code requirements and resources in the state of Alabama, please visit the ADECA website. A link is provided, or you can simply search in your web browser for ADECA Energy Codes, and you should land on the ADECA Energy Division Energy Codes Resource website. The new 2015 Alabama Residential Energy Code will combine parts of the previously adopted 2009 IECC, International Energy Conservation Code, new requirements from the 2012 IECC specifically relating to envelope leakage, duct leakage, and ventilation, and a new compliance pathway called the Energy Rating Index, which is included in the 2015 IECC. Pieces of each of these three code cycles have been combined together to form the new 2015 Alabama Residential Energy Code. What homes or buildings have to comply with energy code requirements? Residential buildings, single family and multifamily, 3 stories and below, need to comply with the energy code. Some buildings, including buildings that do not have conditioned spaces and historic buildings, may be exempt from these requirements. If you have questions about how the energy code will be enforced on your projects, please touch base with your local code official. For builders, there are compliance pathway options. These include following the prescriptive code, following the simple trade-off or U-factor area calculation trade-off approach, or following the Section 405 annual simulation approach, or producing an Energy Rating Index, ERI, that demonstrates the home satisfies currently adopted code standards. Regardless of pathway, you must always comply with the mandatory requirements, and it is within the mandatory requirements that we will find the requirements for blower door, envelope leakage, and duct leakage testing. Here's a picture of a blower door and a duct leakage test. Each of these will now be mandatory under the new Alabama Residential Energy Code, which goes into effect October 1st, 2016. Under this new code, all single-family and multifamily residential structures, 3 stories and below, in the state of Alabama will be required to conduct an envelope leakage test or blower door test, and to achieve satisfactory air tightness of 5 air changes per hour or less at the test reference pressure of 50 pascals. A recently conducted field study in the state of Alabama and other states looked at envelope tightness blower door test results in air changes per hour for observed homes across the state. 65 homes were observed in the field under construction in Alabama for this field study. The results below for Climate Zone 2 and Climate Zone 3 show what was found. The red bar indicates the current Energy Code standard of 7 air changes per hour for a home that is tested. As you can see, in both Climate Zone 2 and 3 in the state of Alabama, the majority of homes being constructed met this 7 ACH 50 test requirement. Here's the same information displayed on a different chart. Here you can see 7 ACH 50 as the red dashed line. You can see that 65 homes were observed They're color-coded by climate zone. And you can see how those homes performed. This green box shows us the homes that would meet the new standard of 5 air changes per hour at 50 pascals. It appears to be roughly half of all of the homes that were observed for this field study. The good news is this means a lot of the homes currently being constructed in Alabama will already pass a 5 ACH 50 blower door test. The bad news is some of these homes would be required to have mechanical ventilation, which may not have been included. How does a blower door test work? Well, the blower door test will be required by the new Alabama Residential Energy Code. It's used to quantify the amount of leakage across the home's thermal boundary. It's administered by a certified professional, and it's reported to the builder or owner and the code official. What does the fan actually do? What we do when we perform a blower door test is to use the fan to create a pressure difference between inside and outside. There's a standard test reference pressure of 50 pascals. This is typically done in negative 50 because we use the fan to depressurize the home. We then measure the fan flow in CFM, cubic feet per minute, so we know how much air is going out of the house. To determine the number of air changes, we multiply the cubic feet per minute measured at 50 pascals by 60, because there's 60 minutes in an hour, and we divide that by the cubic volume of the home. This allows us to determine ACH 50, air changes per hour at 50 pascals. This is the industry standard test reference pressure. A pressure gauge tells you much of this information. In this particular gauge, we can see the left side showing us that we've achieved the negative 50 pascals test reference pressure, and we can see on the right side that we know that there's 4,247 cubic feet per minute of air being blown out of the fan through the blower door at this test reference pressure. What could we do with this information? Well, of course, we can convert it to air changes per hour. Another interesting thing would be to take this information and use it to determine how big the hole in your building's envelope is. There's two ways to do this. The most accurate way is to divide your CFM 50 by 7.495 to get square inches, and divide that by 144 to get square feet. In this scenario, our 4247 would be approximately 4 square feet of opening in your building's thermal envelope, or a 4.5 square foot hole, or a 4 square foot hole. On the other hand, you could use the south face shortcut, which gives you a rough estimation of the size of the hole. Divide your CFM 50 number by 1,000, and you'll have a rough estimate of the size of the hole in your thermal envelope. In this scenario, 4.2 square feet. This information is useful when trying to visualize how big of an issue you have based on your blower door leakage results. So, what is the purpose of ventilation in homes? Primarily, the purpose of ventilation is to provide fresh air for occupants and to dilute pollutants which may build up inside the home. Several questions come up when we discuss this idea of tightening thermal envelopes, testing homes, and then reintroducing ventilation air. One common question is, why get rid of leaks and then add ventilation? Another is, isn't ventilation an energy expense? And a third is there only one way to do ventilation? Well, why tighten up the envelope? In the high-performance building world, we sometimes say, build it tight, ventilate it right. This is the idea that we want to get rid of that large hole, let's say a 4 square foot hole, and we want to replace it with a small hole that does one specific thing, and that is bring in outside air for human comfort and good indoor air quality. The benefits of this is that we eliminate air leakage from uncontrolled, unknown sources, which means that we could be breathing attic air, crawl space air, garage air, and we replace that with outside air. Then we condition that outside air, we filter that outside air, and we provide it to the spaces in the house where we expect the occupants to be. This gives us the best case scenario. We eliminate uncontrolled leakage, we eliminate the potential for pollutants to be drawn into the house through uncontrolled leakage, and then we reintroduce fresh air, which can be dehumidified, conditioned, filtered, mixed, and provided to the zones of the house where we expect the occupants to be. Simply put, build it tight, ventilate it right. How much ventilation air? This is also a common question. ASHRAE 62.2 2010 sets a standard for single-family ventilation, and this is referenced in the IRC, the International Residential Code. You can either do a calculation to determine how much ventilation air your home needs, or you can use a lookup chart which has been provided in the code. The calculation basically says you need 0.01 cubic feet per minute of air times your floor area plus 7.5 cubic feet per minute of air times the number of occupants in the home. And the number of occupants are determined by taking the number of bedrooms and adding 1. So a 3-bedroom home would be assumed to have 4 occupants. You can either perform this math or you can use the convenient lookup table. Let's use the lookup table and say, for example, a 3,000 square foot house with 3 bedrooms would need 60 cubic feet per minute of continuous ventilation. A 2,800 square foot 2-bedroom home would also need 60 cubic feet per minute of ventilation air. On the other hand, a 3,500 square foot house with 4 bedrooms would need 90 cubic feet per minute of ventilation air. Now, if you want to do intermittent ventilation instead of continuous ventilation, you simply need to determine your runtime and factor that in to the total volume of air that you need. For example, if we had a 3,000 square foot house with 3 bedrooms, we would have to provide 60 cubic feet per minute of continuous ventilation air. If we only wanted to ventilate the home for 30 minutes out of every hour, we would have to provide 120 cubic feet per minute for that 30 minutes, and so on. Now, there are multiple ways to do ventilation in a home. The first option we sometimes refer to as exhaust only. This is basically to use an exhaust fan to create air changes in the house, whether it's a single fan or a multiple fan. Another option is what we refer to as supply side only, to bring air, pump air into the house, put the house under slightly positive pressure. And a third option is sometimes referred to as balanced ventilation. We're going to exhaust the same amount of air out of the home as we bring into the home and keep the home in neutral or balanced pressurization while providing air changes. There are pros and cons to each of these options. Some of the cons to exhaust only or negative house pressure strategies are that we go back to introducing air from unknown sources, meaning we might be pulling that makeup air in from a garage or a crawl space or an attic, and we don't have the ability to filter or dehumidify or condition the air that's being brought into the home. Because of this, this may not be an ideal strategy in hot, humid climates. Supply only puts the house under slightly positive pressure, thereby reducing the chance of sucking in air from unwanted sources such as crawl spaces and garages. Depending on how you do this, it may require you to use the air handler to circle air through the house, which can be an energy penalty. On the other hand, you get good mixing of air, you have the potential to filter and condition the air, and you do a good job of delivering it into the zones of the home where you want the house. There are multiple ways to achieve supply side or positive pressurization, and we'll talk about those in more detail in a minute. Balanced or neutral house pressure ventilation often uses an apparatus called an ERV, an energy recovery ventilator. What this does is bring in outside air and use the stale air that's being exhausted out of the home to temper or precondition the incoming airstream. These often do a great job of providing ventilation. They can be ducted into existing HVAC systems, and they often do a pretty good job of recovering sensible load or bringing down the temperature or up the temperature of the outside air by preconditioning it with the exhaust stream. The ability of these pieces of equipment to remove moisture or dehumidify the air varies significantly depending on the type of equipment that you spec. Let's take a look at a few scenarios for ventilation air in the Southeast. Here we have what we're referring to as the Acme Ho. It's in Birmingham. It's 2816 square feet. It's got a downstairs and an upstairs. And we've designed it first and foremost for our base case to comply with the 2009 Alabama Residential Energy Code. So you can see we've got R30 on the ceiling, we've got R13 in our knee walls, we've got an R19 on our any floors and over our garage, typical double pane low-E windows, and compliant duct leakage and envelope leakage numbers, and compliant lighting. We've also applied a 12.5 cents per kilowatt hour electrical rate plus base fees, and $1.20 per hour or per therm rate plus base fees for utilities. So the building that complies with the 2009 based Alabama Energy Code costs $2,626 a year to operate. Let's improve our home to meet the new 2015 Alabama Residential Energy Code. Our performance for our value and windows are going to stay the same. Our duct leakage is going to be reduced, our envelope leakage is reduced, and our lighting efficiency is improved to meet new code minimums. We keep the same rate structure for our utility bills, and we run it through the energy model. What it tells us is that our new home is going to cost less to operate than it would if it was designed to meet the older code. We went from $26.26 a year to $24.41 a year, or we've saved $185 a year in utility cost for this particular model of this particular home. But this does not include ventilation. So let's take a look first at exhaust-only ventilation. Here we have a bath fan. Moves about 80 cubic feet per minute, draws about 23 watts. When we model this, we see that it costs about $51 a year to operate, or approximately $4 per month. And we go from $24.41 to $24.92 in total annual operating expense. Overall, we've still saved energy and utility costs, but we gave back about $51 a year to reintroduce ventilation. The downside to this ventilation strategy is, again, it puts the house under negative pressure, and we may be drawing in our makeup air from undesirable sources, like attics, crawl spaces, or garages. So this will create air changes in a home, but will not necessarily give you control over where your makeup air comes from. Let's look at another option. This is a SupplySide Smart Fan, as it is being called in this scenario, which pumps air into the home. It puts the house under positive pressure, can produce about 60 CFM, cubic feet per minute, at 15 watts, and would probably provide the ventilation needed for a lot of new homes being constructed. Looks like it costs about $275, but it's pretty efficient to operate. About $42 a year, about $350 per month. The benefit of this is that it'll provide the ventilation that we need, the air changes we want in the home. At low cost, we'll also put our house under positive pressure, therefore keeping at bay pollutants that might be coming from crawl spaces, garages, and attics, and will allow us to choose where the outside air is being pulled from, wherever the location of the inlet side of this fan duct is. So this seems to be a pretty good option. What it doesn't do is allow us to precondition the incoming air with the outgoing airstream. A piece of equipment like an ERV, an energy recovery ventilator, will allow us to do just that. Here's an example of an ERV that can do 35 to 70 cubic feet per minute of ventilation air. Does a pretty good job with sensible recovery. That means bringing the outside air down or up to temperature by preconditioning it with the stale air that's being exhausted from the home, and costs us about $7 per month to operate, or $89 a year. This is a great option because it preconditions incoming air with outgoing air, it maintains balanced ventilation, and gives us control of where our ventilation air is pulled from. It does have the highest upfront cost that we've looked at of about $575 just for the unit plus installation. But offers us many benefits, which we just discussed. Another option that we've seen done in many commercial and residential buildings is a central fan return side outside air duct. As you can see in the diagram, we've taken a duct with an inline damper and introduced it to the return side of our HVAC system. There's a controller that determines how many minutes of every hour this duct is open. So you can determine the amount of outside air you need. You can ramp the system up or down for continuous or intermittent ventilation. And when the HVAC system is running, outside air will be pulled in through this duct, dumped into the return side, mixed with the return air from the home, passed over the filter, over the coil, and supplied into the house. This will do a very effective job of mixing and supplying the ventilation air, and it gives you a high level of control. Additionally, it has relatively low upfront costs because the equipment is only about $150. The biggest downside of this system is that it has the highest annual operation cost, about $129 a year or $11 a month. So we're giving back the greatest amount of our energy savings to reintroduce ventilation into the home. It's an option. It certainly complies with the requirements of the code. It gives us a high level of control and a low amount of upfront cost, but it will cost us the most to operate. All of these options are allowable under ASHRAE 62.2 and the Energy Code. Thank you for attending this presentation on ventilation in residential structures. Again, my name is Burke Reeve, and my email is breeve@southface.org. If you have any questions about ventilation, energy code requirements, or looking for additional resources, I encourage you to contact me. Thank you.